In this class, we have already talked about atoms of different elements coming together to form compounds. In this lecture, we will discuss how this happens in more detail. Remember that all compounds can be subdivided into ionic compounds, in which electrons are transferred from one atom to another to form a cation and an anion that are held together by electrostatic interaction, and molecular compounds, in which electrons are shared between two atoms. Let's discuss ionic compounds first. An example of an ionic compound is sodium chloride, table salt. Let us watch the formation of sodium chloride from solid sodium metal and chlorine gas.
We've asked Lonnie to demonstrate the formation of an ionic bond. In this case, the bond between sodium and chlorine in sodium chloride. So Lonnie's filled a beaker with elemental chlorine. That's chlorine gas, Cl2. It's a yellow gas. He'll also use solid sodium metal. Solid sodium metal is a shiny silver metal that's very soft. He can actually cut it with a knife. Sodium metal is very reactive. It will react in air and water, so it's stored under hexane. He'll pull off a small chunk and immediately store it under hexane while he prepares the rest of the experiment. Now, to get the reaction to go, he'll want to clean the sodium, make the surface very clean, and warm it slightly to help the reaction proceed. He'll do that by placing the sodium in a spatula and then warming it over a flame to clean the surface and to get the sodium warm enough to initiate the chemical reaction. The reaction goes because the positive ions formed on sodium and the negative ions formed on chlorine are drawn together, a Coulombic interaction, to form an ionic bond. Now the reaction between sodium and chlorine, of course, forms sodium chloride. We typically know that as table salt.
So what happens to electrons in this synthesis of sodium chloride? Initially, sodium atoms in the metal have all of their electrons. Because the number of negatively charged electrons is the same as the number of positively charged protons in the atomic nucleus, the net charge of the sodium atoms is zero. Because the two chlorine atoms in the diatomic molecule of chlorine gas are identical, the electrons in the chlorine molecule are equally distributed between the two atoms. Each atom has as many electrons as it has protons in the nucleus, so the net charge on each chlorine atom is also zero. Once the reaction between sodium and chlorine occurs, one electron from each sodium atom is taken away and transferred to a chlorine atom. Therefore, a sodium cation with a net charge of 1 plus and a chloride anion with a net charge of 1 minus are formed. This is an oxidation-reduction reaction, since a transfer of electrons from one substance to another occurs, and the charge states of the atoms involved in the reaction change. But why are electrons transferred from the sodium to the chlorine? It turns out that atoms or ions are most stable when they have 8 electrons, referred to as an octet, in their outermost shell. The outermost shell that has any electrons in a neutral atom of an element is referred to as the valence shell. If we write the electron configuration for all atoms in the periodic table, we will find that the noble gases, except helium, have 8 electrons in their outermost shell. Noble gases do not readily react with other elements. Other elements can go to a more stable state by gaining or losing electrons. For instance, sodium has an atomic number of 11. Its electron configuration is 1s2, 2s2, 2p6, 3s1. It has one more electron than neon, the noble gas that precedes it. That one extra electron is the only electron in the third shell. Chlorine has an atomic number of 17. Its electron configuration is 1s2, 2s2, 2p6, 3s2, 3p5. It has one fewer electrons than argon, the noble gas that succeeds it. It has 7 electrons in the third shell. If sodium donates its only electron in the third shell to chlorine, forming a sodium plus cation, then its outermost shell that has any electrons will be the second with a total of 8 electrons. When chlorine accepts the electron from sodium, it will form a chloride minus anion. The extra electron will be added to the 7 electrons in the third shell to bring the total up to 8, so both sodium plus and chloride minus then get stable electron configurations with 8 electrons in the outermost shell, like those of the noble gases, that of neon for sodium plus and that of argon for chloride minus. Note that by donating an electron, sodium does not turn into neon, and by accepting an electron, chlorine does not turn into argon, because the chemical identity of an element is determined by the number of protons in the nucleus that doesn't change. Rather, a sodium cation and a chloride anion are formed. Gilbert Lewis, a famous American chemist who served as a professor and dean of the College of Chemistry at UC Berkeley for many years, proposed a convention for representing electrons in the valence shell of a chemical element, referred to as valence electrons. In this convention, known as Lewis dot structures, valence electrons are shown by dots. The dots are placed on all 4 sides of the symbol of a chemical element, at the top, the bottom, left, and right. 1 dot is placed on each side before a second dot is placed on any side. No more than 2 dots can be placed on any side, so the total number of valence electrons for the element does not exceed 8. So here are the first 3 periods of the periodic table, and here are the Lewis dot structures of the elements in those periods. As we said earlier, the noble gases, except helium, have 8 valence electrons, a complete octet. Helium has 2 electrons in the first shell. The first shell only contains 1 orbital, 1s, and therefore cannot hold more than 2 electrons. Therefore, helium has a completely filled first shell, 2 electrons, and this is referred to as a duet. Other elements can lose or gain electrons in order to obtain the same electron configurations as the noble gases. Depending on the compound that it is part of, hydrogen can lose its only electron or can gain another electron to get a duet like helium. Lithium and beryllium tend to lose 1 or 2 electrons respectively to also end up with a duet in their first shell. Other elements can lose or gain electrons to get an octet. Lewis dot structures offer a convenient method for visualizing how electrons are transferred in ionic compounds. Let's look at how to draw the Lewis dot structure of an ionic compound using the example of sodium chloride. The first step is to write the Lewis dot structures for the metal and the nonmetal, sodium and chlorine in this case, side by side. Then the valence electron from the metal should be transferred to the nonmetal. When this is done, chlorine has an octet in its valence shell, and the valence shell that held sodium's only electron, the third, is now empty, and the preceding shell, the second, has an octet. The final step in writing the Lewis dot structure of an ionic compound is indicating the electric charges of the cation and the anion, given by the number of electrons lost or gained. The anion with its octet is written in brackets, and the charge of the anion is indicated outside these brackets. In another compound, sodium hydride, the only electron in the valence shell of sodium is transferred to hydrogen, giving it a duet. In different compounds, hydrogen can either gain or lose electrons. For instance, in hydrochloric acid, it gives up its only electron to chlorine. Whether an atom loses or gains electrons in a compound is determined by a quantity called the electronegativity. Electronegativity is a measure of the tendency of an atom to attract electrons. Electronegativity exhibits the following periodic trends. It increases as we go right within a period and decreases as we go down within a group. There are some exceptions to this rule. Noble gases that do not readily form compounds, transition metals for which the electronegativity varies relatively little, as well as F-block elements, the lanthanides and actinides, that generally have complex chemical properties. Electronegativity is a dimensionless quantity, meaning that it has no units. It is a property of a chemical element. When considering a pair of elements that form an ionic compound, to determine which element transfers its electrons to the other, it is necessary to compare their electronegativities. The element with larger electronegativity will take electrons from the element with smaller electronegativity. Electronegativity values have been systematically determined for chemical elements in 1932 by the American chemist Linus Pauling. Pauling was one of the most prominent chemists. He was awarded a Nobel Prize in Chemistry for developing the theory of chemical bonding. He also received a Nobel Peace Prize for his advocacy for nuclear disarmament and vocal opposition to weapons of mass destruction. His wife, Ava Pauling, was a civic activist who convinced him to get involved in these issues. Looking at the electronegativity table, you can see that nonmetals generally have larger electronegativities than metals. Therefore, nonmetals accept electrons from metals and form anions, and metals donate electrons to nonmetals and form cations. Now it is time to talk about bonding in molecular compounds, where electrons are not transferred from one atom to another, but rather shared between two atoms. Remember, a molecule is a combination of two or more atoms of the same element or of different elements with a constant composition, well-defined arrangement and properties. Molecules can be homoatomic, consisting of atoms of only one element, or heteroatomic, consisting of atoms of more than one element. An example of a homoatomic molecule is white phosphorus, P4. An example of a heteroatomic molecule is water, H2O. Most compounds that consist entirely of nonmetals are molecular compounds. In molecular compounds, electrons are not transferred from one atom to another, but shared by two atoms. This type of bond is called covalent, because in homoatomic molecular compounds all atoms are identical. There is no reason for electrons to prefer being on one atom over another. Therefore, electrons are shared between atoms rather than transferred from one atom to another. In heteroatomic molecular compounds, electrons may be shifted more towards one of the elements and away from another, but they are not transferred completely. The degree to which electrons tend to be closer to one of the atoms in a covalent bond than to the other is called the polarity of the bond. A bond is considered nonpolar if the electronegativity difference between two atoms is less than 0.5, and polar if it is greater than 0.5. To draw the Lewis dot structure of a molecular compound, place atoms that make up the compound symmetrically. For instance, for a water molecule that is made up of one oxygen atom and two hydrogen atoms, place the oxygen atom in the middle and the hydrogen atoms on either side of it. Write the Lewis dot structures for all atoms, placing the unpaired electrons between the atoms. Then pair up the lone, that is the unpaired electrons of two atoms, placing them between the atoms, so that every atom except hydrogen has 8 electrons, whether its own or shared with another atom, and each hydrogen atom should have 2 electrons, whether its own or shared with another atom. Electron pairs that are between two atoms are counted for each of these atoms, and then these electron pairs are replaced with dashes that represent bonds. Here are a few more examples. For carbon dioxide, place the carbon atom in the middle and the two oxygen atoms on either side of it. It turns out that if carbon and each of the oxygens share just 1 electron with each other, then the number of electrons for carbon is only 6, and the number of electrons for oxygen is only 7, short of an octet. Therefore, carbon and each of the oxygens share 2 electrons with each other. Each of the shared electron pairs is replaced by a bond. This is what's known as a double bond. For hydrogen gas, H2, a homoatomic molecule, each hydrogen atom shares its only electron with the other hydrogen atom, so each hydrogen has a duet. For nitrogen gas, N2, each atom in the homoatomic molecule shares 3 of its electrons with the other in order for each of the 2 atoms to have an octet. The 3 shared electron pairs form what is known as a triple bond. The octet rule, the requirement that each atom in a molecular compound except hydrogen has 8 electrons, whether its own or shared with another, and that hydrogen have 2 electrons, usually holds, but it's not universal. A prominent exception to this rule is boron, the only nonmetal with 3 electrons in its valence shell. Boron tends to only have 6 electrons when it forms compounds. It shares each of its 3 electrons with another atom. Examples of boron compounds are boron trihydride or boron trifluoride. You can see that boron has 6 electrons in each of these compounds. In some molecules, a central atom may have more than 8 electrons. This is referred to as an expanded octet. Examples of compounds with expanded octets are sulfur hexafluoride, 12 electrons for the sulfur. Phosphorus pentachloride, 10 electrons for the phosphorus. Such compounds can only be formed when the central atom is one of an element that is in period 3 or greater. Finally, there are some other exceptions, particularly for molecules with odd total numbers of valence electrons, like nitrogen monoxide. It has 11 valence electrons, 5 from the nitrogen and 6 from the oxygen. This compound exists in nature even though the nitrogen atom only has 7 electrons in it. The oxygen has 8. Exceptions to the octet rule occur because Lewis dot structures are a really simple representation of a rather complicated chemical reality. In the following lectures, we will talk about using Lewis dot structures to determine the shape of molecules. The basic idea for this task is that bonds, whether single, double, or triple, and lone electron pairs, that is, electron pairs on an atom that are not part of a bond, arrange themselves so as to be as far from each other as possible. If a central atom has only 2 bonds and no lone electron pairs, these bonds can position themselves opposite one another, with an angle of 180 degrees between them. This molecular geometry is called linear. An example of a linear molecule is carbon dioxide. Carbon does not have any lone electron pairs in carbon dioxide. If a central atom has 3 bonds and no lone electron pairs, in order to be as far from each other as possible, the bonds must point towards the vertices of an equilateral triangle at angles of 120 degrees to each other. This molecular geometry is called trigonal planar. An example of a trigonal planar molecule is boron trihydride. If a central atom has 4 bonds and no lone electron pairs, to be as far away from each other as possible, the bonds must point towards apices of a triangular pyramid at angles of 109.5 degrees to each other. This molecular geometry is called tetrahedral, and an example of a tetrahedral molecule is methane, CH4. If the central atom has lone electron pairs, these pairs need to be accounted for when deducing the molecular geometry. Lone electron pairs need to be positioned as far as possible from bonds and from each other. For example, if a central atom in a molecule has 3 bonds and in addition 1 lone electron pair, then the bonds and the lone electron pair must point towards the apices of a triangular pyramid to get away from each other as far as possible. Therefore, the 3 bonds are not in the same plane. The angles between them are 109.5 degrees, like in the tetrahedral geometry. But there is no 4th bond. Instead, there is a lone electron pair. This geometry is known as trigonal pyramidal. An example of a trigonal pyramidal molecule is ammonia, NH3. If a central atom in a molecule has 2 bonds and 2 lone electron pairs, then the bonds and the lone electron pairs point towards the apices of a triangular pyramid. Therefore, the 2 bonds are not opposite each other, but again at an angle of 109.5 degrees. This geometry is known as bent, and an example of a bent molecule is water. The following slide summarizes the various possibilities for molecular geometry.